Hey everyone, in this short video we're going to spend some time in KiCad and we're going to learn how to make our first PCB. This example is tied to some in-class examples that I did in my junior design course. So hopefully the schematic's familiar for those of you in that course, but for the rest of you, basically what we're going to do is we're going to use an LM386 op amp and a couple LEDs to make a sound and light board that can attach to an Arduino Nano. Here on the screen, you can see I've already loaded KiCad and I've loaded the in-class example. You can also find a link to the in-class example down below in the comments section. From here, I've already started a schematic and a PCB. So we'll be working from those. Whoa, there we go. We're working from those. So real quick, as an overview of the schematic, it's not our focus, the design. I've already added a barrel jack. I've added the Nano itself. I've added the audio amplifier, and this audio amplifier is designed based upon one of the application schematics in the LM386. And I've added two of what I hope to eventually be 3 LEDs. So our first step, whenever you're designing a PCB for the first time, is to make sure that your schematic is right. Using software EDA tools, electrical design tools, you always have the schematic and the PCB linked, which means that as long as your schematic is right, your PCB really can't be wrong. You can design it in a way that isn't as effective or as efficient or might not meet some of the frequencies, but it'll at least be electrically connected correctly. So it's important to start from the schematic. A couple things that are pretty important here. In KiCad, you can set a grid. We're doing this in a US institution, and so we're going to go ahead and stick with our English units here. And I've turned on my grid. I can update and I can change the grid that's being used under the, where was it? View grid settings. And so here I can set my grid size. Okay. I choose a large enough grid that it's pretty easy to move things around and then align the wires and the net connections. The other thing that we're going to see here that's pretty useful is I use this concept of connected nets. So most schematic tools have the ability that if you have a named net, in this case VIN, it'll be logically connected to every other spot that's labeled VIN. So here's another spot and a third spot. Similarly, we can connect signals, and in the case of ground, most software tools also have the ability to put a very specific shape down, and that shape will connect. This really makes it a much nicer layout rather than drawing wires every which way. Another thing that's pretty important when you're laying out your schematic is to make sure that things that aren't supposed to be connected are marked that way so that you don't forget to do something. As I mentioned, you always want your schematic to be right before you spend a lot of time on your layout. So in this case, I would want to be sure that I was ready. And so I've noticed that I have a couple pins here that are not marked as no connects. KiCad uses this X symbol, which is available over here from the side. So I would either want to make these marked as disconnected or use them. In this case, all I want to do is I want to add a couple LEDs, all right, specifically one more. So I could browse and find this LED using the part selector tool. KiCad will load all of the libraries that are built into it or that have been downloaded for it. And in this case, I could then go ahead and I could look for a new LED. And it provides some examples from different libraries. So in this view, what I'm seeing is I'm seeing the library name, and then within it, there's something that matches the LED that I've entered in the search term. This particular component library is something that was developed internally by myself. Other libraries, though, are available with the default download of KiCad. So you will definitely see the device. And from here, you have a couple different versions of LED. I'm using this LED alternate because I want to make sure that, well, not make sure, I prefer this symbol where it's solid to this symbol with this weird line through the middle. But it's just a visual difference, really nothing more significant than that. So if I want to add this alternate one, I can go ahead and place it down. R for rotate, or right-click rotate, as the case may be for orientation. Okay, these are our keyboard shortcuts in KiCad and make it very fast for you to do the design. All right, and then that would want me to put another one. I'm done putting down those parts. Another way I can add a part, and something that I think is super valuable, is I can copy a part. Why is this important? Well, if I look here, this one that I put down fresh and new doesn't have a value. Okay, LED alt, that's kind of the default number. Whereas this one's value is blue, and that's because I manually made it. Similar, this resistor R1 has a value 220 ohms. And if I dig even deeper, so a right click reveals this menu, and I can adjust properties, okay? And I can edit properties. So in this view, I've already assigned a footprint. A footprint is the shape that is actually laid down on the circuit board. I've also already picked a very specific part to be purchased to fill this need. And so if I copy this one, all of this information is copied, okay, rather than having to manually enter it again. So I'm going to hit the C key, or I could right-click copy. There we are. Duplicate is the term that KiCad is using, but the C key basically does that. So I'll just mouse over it and hit C, and boom, I have another one. And this one already has all of those values inherited. You will notice that the R has a question mark, and we're going to fix that in a second when we do what's called annotating the design. So I'm going to spend a few moments kind of laying this out and making some connections, and then we'll move on to our next step. Okay, so now we have our 3 LEDs, at least starting points for our LEDs, but we haven't yet annotated them, i.e., as well as resistors, given them a reference designator. So this is replacing the question mark with a number so that the KiCad software knows that it's a real part and has a unique identifier so that we can begin to give it information. The only other thing I want to do on this design is I want to add a bulk capacitor. And so in this case, I'm going to copy this 330 microfarad that's already in use, and then connect it up to VN and ground. And this is just to make sure that whatever I plug into the system, if I have an audio signal, which I will in this audio device, I have good clean power for supplying it. And you'll notice that I'm just kind of grabbing these. What's happening on my keyboard is I'm pressing C for copy on each one of these, and it's just taking a copy of whatever I've clicked on. And I'm using W to generate a wire. Just to see that, a right click, begin wire, and then end wire. There we go. So this 5 volt and 3.3 volt power here, this is actually an output of the nano board, and it's generated whether or not you power the nano from a USB that's plugged in or from this VN pin, because the nano itself has a built-in voltage regulator. I could tie those to something so they'd be available for some add-on or build-up I might do, but in this case, I'm going to go ahead and just leave them not connected, because I don't think I'll use them in this design. So at this point, everything's in place. I'm going to go ahead and save, and then I'm going to do the annotate. So the steps of the PCB kind of run along this pathway here on the default install of KiCad. So first step is to annotate. It's asking me what I want to annotate, what I want to do, how do I want to assign the numbers like R1, R2, R3, the order of those. It's asking me if I want to re-annotate everything or keep any annotations that are existing. In this particular case, since I've already started a layout that we're going to be basing our video on, I want to go ahead and keep those existing annotations. And then I want to see anything that goes wrong. So annotate. I look here and it looks like it added some new annotations to the ground symbols I added. It made C2. It gave a D3 assignment to this LED, which was the new one that we added. It added some annotations to resistors. Okay, and it's done. So at this point, I hope that I have a completed schematic that I can use for my board design. I'll save. The next step is, in order to know what goes on the board, I need to connect to each of these parts the footprint to be used on the PCB. So for example, this resistor could be on my board a through-hole part or a surface mount part. This LM386 chip could be a surface mount or a through-hole. Those parts could also be different versions of through-holes or different versions of surface mount. For example, the resistor comes in very small parts like an 0402 surface mount to very large parts like a 3-watt through-hole resistor. Anything in that range could be what I put onto the layout. So I need to tell the software what do I want to have on the layout. That's done through assigning packages or PCB footprints. So I'll bring up this tool. It's loading in the background. It's a little slow on many machines because it's loading a lot of libraries and images to be able to let me do this process. All right, so here I've loaded the interface. It looks something like this. What you can see in this Assign Footprints interface is in this first menu bar, we have all the different libraries that are available. And these are specifically footprint libraries, not schematic symbol libraries. It's important to realize that everything in a software development tool has both a schematic symbol and a footprint. And then there's some linkage that says which pins of the schematic match which pins of the footprint. And so in this case, that's what these little numbers are. So these little numbers that are next to each one of these pins are not necessarily the pin number that is on the integrated circuit, but they're used to link which pin of the integrated circuit is in place. Now, normally they match 1 for 1, but that's not always the case. Okay, so back to our assignment tool. Another very useful piece here is I like to always turn on this footprint viewer because it kind of gives me a handle on what it is that I'm looking at. And so in this case, I've highlighted this nano, and so it's showing what it thinks is that part versus this through-hole capacitor. Okay, so let's talk about this right window. So what this right window is it's a filtered version of everything from the libraries that we're allowing to be seen. All right. So there's a couple filtering options. So for example, I can say only show me things that have the same number of pins as my schematic symbol. This is a 2-pin capacitor. Therefore, it's showing me everything that has only 2 pins. So that's where I'm getting battery connectors in here. Now, it's also only showing me battery connectors because I'm only looking at the current selected library. So if I want to look at every 2-pin connector in this card library versus the coaxial, I can pick what's being displayed as a possible input. If I want to look at all libraries, I can turn off the library filter, and here is everything in all libraries that has exactly 2 pins. Okay. So this is pretty useful if you're not sure the footprint. It is your job as the engineer to be sure that you've picked the correct footprint for the part, and sometimes you even have to look it up. So we're going to do that together. So one of the more interesting parts is this barrel jack. So this barrel jack does not yet have a part assigned to it. Let's go ahead and poke at the schematic so that we can see what that looks like real quick. It's here, and notice it turned red. And it's actually an interesting part because it's a 3-pin device where this pin 3 is a switch. So when something's inserted, you could detect whether it's inserted or not. Now we don't need that feature. We're just going to use this barrel jack as a power and ground input. But we still need to find a part that we can use for it. So jumping back to our views for that. Okay. We're going to pick the barrel jack switch. We're going to look in all libraries for the right number of pins. And at this point, it's a matter of finding something that seems similar. You can always make your own layout, make your own part. But luckily, KiCad supplies some starting points. And if one of these works and the part's available, that might not be a bad idea. So I'm finding there's specifically a library called connector barrel jacks. So hopefully one of these is something that works for me. I find that there's a surface mount variant here, some more surface mount through hole. So notice on this viewer, this one has a clear hole in the middle of the pad. That helps me know it's a through hole part. And in this case, it has slots. Okay, another through hole part, another through hole part, another through hole part, and another through hole part. Okay, I'm going to go ahead and go with a through hole for this. There's a lot of reasons why I would choose one over the other. One thing about through hole parts is when they're soldered in, they're usually more mechanically stable. And this is the part I want to choose. And the reason I'm choosing it is built into the name is the part number. So KUI is a company that makes parts like this, and this is their model number. Okay, and you might not know that starting out, and that's fine. One thing I've really liked about the open source libraries that KiCad supplies is that they use a standardized naming structure, so it becomes pretty clear what something is. And so this is a horizontal mount, and it's this particular part number made by this company, and that'll be echoed. So here it's Cliff is the manufacturer, there's the part number, and it's surface mount, and it's horizontal. And so you can see that that's carried through. This one here, I would love to use this part or could use this part, but I don't know who makes this part. I don't know where this came from. And so because of that, I'm a little suspicious of it and that I could find something that would plug into it. So I'll start with this one. And this is the PJ102AH. So next thing is let's make sure I can get that part. And I've already done that for the majority of these, but we're going to check together on this one. So here I have a window, and I'm just going to type that in. In fact, I've already typed that in recently. And so here I'm getting some options. It looks like it's available at DigiKey. I always like to go to DigiKey when possible. And PJ102AH, there it is. A bunch are available and can ship immediately. This is an important thing, especially if you're in a time zone or a timeline where parts are long delay. You want to make sure that before you make the PCB, you can actually get the parts in hand. Otherwise, you have a PCB and no parts to put on it. So it is available. One other thing that I might want to do is load the data sheet and actually confirm some information. I'm trusting the library that was supplied to me to be correct, but that's not always the case. Or if I was designing it myself, I would want to be sure. And that's literally looking at mechanical drawings. It'd be a real quick thing to check on this one. So what I'm going to do is I'm just going to check that these two pins here, which are 2 and 1, so front to back, 2 and 1, are 6 millimeters apart. So that's just 3 millimeters and 3 millimeters. And we'll at least check that one thing. And if that's true, then I'm just going to say it's good enough. So I'm grabbing the measuring tool, getting right to the middle of the pad, clicking and dragging, and it looks like, it's kind of hard to see, but in light gray there, it shows 6 millimeters. So I'm pretty happy with what's going here. So I'm just going to assume that I'm correct, and I'm going to double click to assign it. So there I have a barrel jack. Similarly, I need to assign the other parts that haven't been assigned yet. So you'll see my 2 new LEDs, but you'll notice my resistors are already assigned. And that was because I copied them from before and pasted them. But the LEDs are not. Now, the other LED we have already has a layout. It's a 5mm LED. I'm going to assume that I can find a part in that same design just to move forward to layout. So I picked it. And that's in the library LED through hole. So LED through hole. And it's the LED D5. There it is. So now if I select that one, I can assign the same footprint for the other 2. And the final part to assign is this connector. It's a 1x2 female is what it's showing in the schematic. And just to be clear, that's this output connector that will eventually go to the speaker. One of the most common sizes for this, or one of the most common connectors used, is a header pin. And so I'm going to go ahead and look in the connector pin header, and the most common spacing is 0.1 inch. And so all of the ones here are in 2.54 millimeter, or in millimeters, so that's the equivalent to 0.1 inch. So I'm looking only in this library, and I'm looking for anything that only has 2 pins. My options are available here. I have a horizontal mount. So if we can see from the image, it looks like it's laying down. We have a vertical mount. So it's probably pointing up and looking at us. We have surface mount. We have a lot of other unique variants from there. But we're going to stick with the most basic, which is a 2-pin vertical. Now everything's been assigned. So I go ahead and save. Close this out. Open up my schematic again. And make sure everything's saved. So at this point, we can move on to our PCB. So I already have a PCB started, so I'm going to load it up and look at it. And this version of the PCB is missing some parts. So we're missing some of the new parts that we've added. We don't have a board outline, things of that nature. So what I'm going to do is in the schematic, you didn't see what I was seeing because it was in the wrong screen. So here we go. This is what I've kind of started. And so I have some parts available, but I don't have the new parts that we've added. See, I only have the blue LED and 1 capacitor and no plug-in. So what I'll do is back here in the schematic, I need to create a netlist. Generate the netlist. Okay, I'm just going to use the default name. And the netlist is actually how we communicate between the 2 tools. So once that's been generated, I can jump over to the CAD tool, the layout tool, and I can load the netlist I just generated. Okay, so I'm going to load it up, and it's giving me some things that are going to happen when I click apply. That's going to add a new symbol. It's going to add a new footprint. So I'll go ahead and update that. And so now here are the parts that did not exist before. So it's my job to lay these out. And so I'm going to go ahead and do that pretty quick. And I'll be back in touch once I've kind of done that. I am going to try to put these parts in a way that makes sense, kind of paying attention to how things would plug in or not. Also, I'm going to try to minimize the length of the white wires whenever possible. Okay, so what I've done here is I've done a very quick layout. I have my 3 LEDs stacked. I have my connector for my speaker, and then I have its capacitor, and then here's my power input and its. What I'm going to do next, I'm going to draw the board outlines. So to draw a board outline, let's talk a little bit about this interface. So I have the ability to turn off and on a grid, set my units of measure along this side, and basically change my views in my interface. This side allows me to place things that are going to be on different layers of the board. In this particular case, we are doing a 2-layer board. So we only worry about the front copper and the back copper. We could configure this to be multiple layers if we wanted to. We've set our grid to be 25 mils. Again, if you're going to be doing production in the US, it's more common to see mils than millimeters for your layouts, though that is changing over time. We're also going to set how wide our traces are. And so that's something that can be configured, and we're going to do most of our tracing in 10 mils. One of the things you're going to see as I lay out this edge cuts is because I set my grid to 25 mils, it's very easy to make my edge cuts touch each other at the corner. So I'm going to add the graphic line to edge cuts, and I'm going to start right here at the corner, maybe a little out from the nano. You can see the yellow line that I'm drawing out. Now what I want to do is I want to make sure that my parts are all on the board. I'm going to leave my capacitors, however, hanging off the edge because I don't need to spend money for that bit of PCB if I didn't want to. And this is an important thing to remember, is that your PCBs you usually pay by the amount of material used. So, and then I touch the edge of the nano, and then I'm going to double click on my starting spot. Oops. And I now have what's called a board outline. So when I go to manufacture this, this board will be trimmed to that size. Next step is to start routing our traces. These white lines represent connections that should be made. Now, this is a very simple board, and so I'll have lots of room to run traces. But one of the first things I'm going to do is I'm going to add a ground plane to the back side. There's reasons to do that and not to do that. In this case, I'm doing it to make it simple for myself because I don't want to have to run those extra traces. And as we've learned in our junior design course, having a good solid connection to ground can prevent some noise from occurring. So to lay that out, I'm going to put in a filled zone. And I'm going to make sure I'm starting on the bottom copper, filled zone. And when I click initially, it's going to start asking me questions. So it's asking me here, what layer do I want to put the fill on? And what net do I want to connect it to? In this case, I want it to be a ground plane. So I'm going to select ground. And then from there, I'm ready to move forward by, just like with the edge drawings, drawing where this plane can be. Now, I don't need to worry about whether or not I'm covering something that isn't ground, because the software will double check what I'm doing when I do my design rule check, and it'll make sure that I haven't shorted something out that I'm not supposed to. And if you noticed, a bunch of white lines just disappeared. And so that made this layout very simple by comparison. So let's go ahead and run some traces. I'm going to start by working on the top, the front copper, because that's where my parts are. And I'm going to go ahead and draw a trace. So trace, trace, trace. Okay, now this is only a 10 mil trace, which might be small for what you're doing. It might be large enough. But what's neat about this is because I'm using a software tool, watch as I try to put this where it shouldn't be. It won't let me, and in fact, it'll do its best to automatically choose how to make a connection. Now, it's not always smart, as you can see here, but in general, it does a pretty good job of making a good, smooth connection. Okay. If I wanted to have a thicker trace, I might choose a thicker trace, and then I can use it to run my routes. So why would I want to have a thicker trace? It could either pass more current, or it might also be a little more secure when I'm going to learn to solder these for my first time. So I'm just going to run over these with this thicker trace. But what about ground? So this pin is supposed to be connected to ground, and that ground is on the back side. So how do I do that? So this brings up the concept of a via. So if I highlight ground, bring it over to an edge, and right click, I have the ability to place a via. And what a via does is a via connects two sides of the board together. If the back side is all ground, then by putting a via here, double click to connect, it will connect through the board to the ground on the back side. Okay. So now, if I want to go ahead and connect this center point to this pin, go ahead and again continue to draw. I'll pick it out. Uh-oh, it looks like I can't fit through this gap. And that's because of my thickness of line combined with my offset. So if we zoom in really close, you see this yellow circle, both on the top and the bottom? Basically, that's my keep out. And looking at my red line, it can't fit through this little gap. So this is a case when I might want, I might want to go to a thinner track or a thinner trace if I want to have a more direct routing. And there you can see it fits through easily. Okay. From there, I'm going to go ahead and close off all the rest of these lines so that we can move into how to order. Okay, so at that point, I think we're ready to kind of check our design. So I'm going to make sure I get a good save on it. And then similar to how in the schematic, we kind of went left to right. So here we've loaded the netlist. Next would be we could update the PCB. So I had loaded it, but we could just grab it without doing that intermediate step. And then the final step would be to do a design rule check. So your design rules, you want to make sure that what you're designing matches the rules of the manufacturer you're going to use. For this video, we're going to use OSH Park, which is a local fab house here in the state of Oregon. So let's go ahead and see what their design rules are. You could do this with any group or any company, but this is what we're going to use for finding the information. So that's OSH Park. And here we're going to dig around and try to find the design rules we need. Under services, they can do a prototype design. And under that, if we dig down, we find information about this manufacturing process. We find out what materials are being used. We find out thicknesses. We find out the type of copper that's used for their prototype. We find out, then here we get into the specifications. So here they're saying that to do this manufacturing, we must space our traces at least 6 mils apart. And our smallest trace can be 6 mils, nothing smaller than that. The annular ring is the information about how big the ring is around any hole, and this includes vias. And so we have to have at least 5 mils of copper around the hole to be sure that it actually connects. We also want to make sure that we don't have any copper specifically within 15 mils of the edge of the board. As long as we follow these rules, this company is saying that our board will be manufactured as we expect it to be. So the important ones for us are going to be this trace spacing and width, though all of these are configurable within KiCad. So that's the one we're going to go look at together. So to get to our design rules, we're going to load up the always hard to remember because it seems like it moves. It doesn't, but it seems like it does. Try our board setup. So here we are under our board setup. We have design rules. And so here is our overall rules. So this is set up so that our minimum track is already 7.87, so on and so forth, mils. And this could be set as low as 6, according to what OSH part can produce. In our case, just to give us a little bit of room, we'll go ahead and go to that minimum to make sure we can do it. All right. Minimum via diameter. So this is the annular ring plus the minimum drill size, which is information I said we're not going to worry too much about. But is something we can find from the page and we should have. Additionally, we can set the default. Okay, so this is overall all nets on the board. What is the clearance do we need to have? What is the distance between the different pins or between the two different traces? And so we said that that can be as small as 6 mils clearance. So we're going to add that as well. So now you kind of maybe just saw it flicker. Some of these yellow outlines moved. With this being properly set, we can check to see that we've met all the design rules. Track width of 6 millimeters. Okay. Also, we can refill the copper. So we're just going to run the DRC. So we have a couple problems markers. We don't have anything that we forgot to connect, which is great. But we do have these concerns. So let's look at these courtyard overlap. So zooming in, see this little arrow? KiCad is showing where the problem is. And the problem it's having is that the footprint for A1 and the footprint for R2 overlap. And that kind of makes sense because in this particular design, because I knew the nano sat up in the air, I actually put some resistors underneath of it. And so naturally it's saying, hey, watch out. So I'm okay with those two errors. So I'm not going to do anything about them. The other two errors it's having is here under the LED. And it's saying that this little box and this box are overlapping. So basically they're beginning to encroach on each other. Again, I think that that's going to be okay. So I'm not worried about those errors. So those are the only 4 errors that I observed. So at this point, I think I'm ready to go. So I'm going to go ahead and I'm going to save it because this board is ready to be built. Again, using OSH Park to do the board build, all I need to do is bring up that window and upload my files. So going back to the beginning, I'm going to browse and upload. And in this case, I want the PCB file. And then most manufacturers, the next step is that they render your design. So you can kind of double check it looks like what you expect. And here I can see that, yes, the board edges are where they are. I can see that my 2 capacitors hang off the side like I expect. And my jack sticks up. Okay. So all of this seems to match what I'm expecting. And then I could move forward with the actual purchasing process. It's a pretty basic process from there, just like any shopping cart. there's usually a step where you would want to attest that your design is ready to go so they don't manufacture the wrong design. Okay, so that's a brief overview of making your first board, starting from arguably a reference. There are a lot of good YouTube videos out there to do this yourself, starting from different points in the process. But hopefully this helps you if you want to make your first board. I really recommend you try this out. Just spend an hour and a half or so following along and doing what I did. And then with the parts you have from our junior design course, you'll be able to have your own little board that you built yourself and prove to yourself that you can do it. All right, thanks.